Welcome to the CompSci 201 Section 40 lecture for Monday, April 11th. Let me share my application and we will get started right away. Okay. We'll get to the slides first. Today is a discussion of recursion. It's part 2. We're going to recover the basics that we talked about last time. And then we're going to add some new material and cover some examples. Administrative notes, there's a few things to know. Project 1, if you're watching this on Monday the 11th, is due by midnight tonight. Please make sure you get it in by then. Project 2 is now available on GitHub. We'll talk about it briefly. I'll have a separate video that talks about it in more detail. Homework 6 is also now available. It is due next Monday. That is the 18th of April, before midnight. It is on recursion, and recursive programming. So we will talk about that at the end of this video as an example. Now, what I want to do is talk about a quick review of last Wednesday's lecture, where we introduced recursion and recursive programming. From that lecture, we talked about what a recursive function is. When a function calls itself, that is, the function body contains a call to that same function, that is called recursion or recursive programming. It turns out to be a very useful way to solve certain problems. For example, the kind of problems where certain things have to be done over and over with slight differences between them. Previous to this topic, we've learned iteration or iterative programming. Iterative programming is simply using loops to do things over and over, possibly changing, possibly not. Now, I mentioned last week, and this is a good thing to know for an exam, that every programming problem that can be solved with recursion can also be solved with iteration. Iteration, loops, is more general than recursion. So if that's the case, why do we cover recursion? Simply because some problems naturally lend themselves to recursion. It makes the problem easier to solve. Okay, that's an important thing to know. This is why we do this. For recursive programming to work, we have to have 3 conditions. Okay, the first condition, again, we talked about this last Wednesday, is that there has to be at least one base case. A base case is a problem that is so simple we can solve it directly. Just do this and you're done. Calculating 1 factorial, for example. 1 factorial is simply 1. That's a base case. There can be multiple base cases in any particular problem. That's okay. There can be more than one. There just has to be at least one. So that's the first of the 3 conditions. The second of the 3 conditions is that there must be at least one recursive case. Now, a recursive case is that particular situation when the function calls itself, but with a simpler or smaller input. That is a slightly simpler version of the same problem, a slightly smaller input. Instead of 8 factorial, we're calculating 7 factorial because that's, 7 factorial is a little simpler than 8 factorial, and so on. The recursive case must eventually get you to a base case in order to eventually solve the problem. So our first requirement is there must be at least one base case. Our second requirement is there must be at least one recursive case, and the recursive case is only valid if it eventually leads to a base case. The third condition, and this is something sometimes people forget in their haste to solve problems recursively, is that the base cases and recursive cases eventually have to get you to the solution for the problem you want to solve. If you are trying to calculate the factorial of an integer it won't do you any good if what your recursive program does is decide if a string is a palindrome. You actually have to get a solution to your problem. So if you're going to have recursion working, at least one base case that you can solve straight away, at least one recursive case that gets you to a simpler version of the problem, and then eventually the base cases and recursive cases work together to get you an answer to the problem that you have. Here is an example I mentioned briefly last Wednesday. We are going to determine if a string is a palindrome. Now, palindrome is simply a string that's identical forwards and backwards, starting at the string sub 0 and going all the way to the end, string sub -1, you have a particular pattern. If you start at the back, string sub -1, and work your way all the way back to string sub 0, that's going through the string backwards. It's a palindrome if those two things lead you to identical strings. So for example, I have the string BAT-TAB, bat tab, meaningless, but it is a palindrome. It's spelled the same forwards and backwards. The word cat, of course, is not a palindrome because forward it's CAT, backwards it's TAC, and TAC and CAT are different. Okay, that seems to make sense. Different strings, so that is not a palindrome. So what we're going to do is we're going to write a recursive function as part of a program that determines whether a string is a palindrome or not. And then to show you the difference, I'll end by writing an iterative function to show you that you could do the same thing iteratively. The function we're going to write recursively is going to have one parameter, the string. We're going to say, is the string a palindrome? And we're going to have one return, specifically a Boolean. We're going to return true if the string is a palindrome and false if it's not. So the hardest part of recursive programming for many people, no matter how much experience you have, it's just something you have to get used to, is you have to identify your base case or base cases, and you have to identify your recursive cases. So for our palindrome problem, what is the base case? The base case is that a string that is 0 or 1 characters long, by definition, we're going to say is a palindrome. I mean, if it's 0 characters long, it's an empty string forward and an empty string backward are the same thing. And a string that's 1 character long is also a palindrome. The letter A is the letter A forwards or backwards. However, there's another and very important base case, which is if I take a string and I compare its first character and its last character, if the first character, the sub-0 element, is different from the last character, the -1 element, then this is not a palindrome. So in our example of the word cat, the string cat, right, the first character is a C, the last character is a T. Since the first character is different from the last character, this is not a palindrome. So here are, depending on how you want to count them, either 3 or 2 base cases. It depends on how you want to code it. But we have to account for both of them. Okay, so those are our base cases for a palindrome. What about our recursive case? Well, we've covered the case where it's 0 or 1 character long. And we've covered the case where the first and last characters are different. That leaves us the case where it's more than 1 character long, and the first and last characters are the same. So if the first and last characters are the same, that's our recursive case. What we're going to do is we're going to throw away the first and last characters and look at the substring. What do we have left when we throw away the first and last characters? Because if that's a palindrome, the whole thing's a palindrome. If that's not a palindrome, the whole thing is not. Okay? So for example, if I have the 3-letter string yay, the word yay, the first letter is a Y, the last letter is a Y. These are the same. That puts our recursive case in play. Remove the first character, remove the last letter, look at what's left. What's left is the letter A. This is a palindrome. So therefore, we think we have enough pseudocode to we think we now have enough pseudocode to write the program, so let's do that. And from that, we are going to switch, if I can make this work correctly, to PyCharm. And we're going to write this code. Now, all this will be posted to the GitHub. Both the slides and this coding file will be posted to the class GitHub with everything else that's also there. You can follow along or go back at any time. By the way, if you have any questions, if anything is not clear, feel free to contact me, email or DM on Discord, or put a question in the Section 40 channel, and we can try to clarify anything that's out there. But first, our recursive version of the palindrome problem. I don't type any better on virtual meetings than I do in the classroom. It's just preserved for a long this time. So the function is going to be called isPalindrome. And it's going to have a single parameter, which we call phrase. And we'll lay out our comment block. And I have mistyped this. Okay, parameter phrase. This function recursively determines whether a string is a palindrome that is the same forwards and backwards. The parameter phrase is the string we are checking. And the return, a Boolean true if, should spell that correctly, if phrase is a palindrome, and false if it's not. Okay, before we get to that, we're going to go down to our main program and write that. The main program is going to be very simple. Word equals input, enter a phrase to check if it is a palindrome. Okay. Answer equals is palindrome word, print answer. Okay, so now let's go back to our recursive function. Let's write the code first for the base case. Okay, if this is a 0 letter, an empty string, or a 1 letter string, we know that this is in fact a palindrome. We will return true. We can address that, we can code that by simply saying if length of phrase is the name of our parameter, is less than 2, less than or equal to 1, whatever you want, return true. And I have to spell return correctly. Now, our other base case is that if the first letter and the last letter are not the same, in fact, strictly speaking, it's the first character, it could even be a digit. If they're not the same, we're going to return false. This is not a palindrome. So if phrase sub 0 is not equal to phrase sub -1, and -1 is always the last character, if the first and last characters are different, it's not a palindrome. Okay. So in this case, we would return false. That's our base case, two or three, depending on how you want to count it, base cases. Now write the code for the recursive case. And from our pseudocode, we said that we can get the value of the phrase with the first character and the last character stripped out. So this should be is palindrome of phrase sub 1 to -1. Okay. So this is our recursive call. Strip the first and last character off. That's what this does. This strips the first and the last character out. The answer for the string is the answer for the substring. Whatever the answer was for the substring, that the answer is the same for the whole thing, the whole phrase. Okay, because we already know that the first and last were the same. Okay, let's go ahead and run this program. Enter a phrase to check if it is a palindrome. Well, we had in the example in the slides, BAT-TAB. That should be a palindrome. And in fact, it is. Let's run it again. And when we run it again, let's enter our old friend cat. And we are properly told that this is not a palindrome. Okay, this is not particularly useful coding. What I want to do is I want to add some code up front. Make sure the user understands what's going on. Print the current phrase is phrase. Input, hit enter to continue. All right, let's run this program now. Okay, enter a phrase to check to see if it's a palindrome. Let's go back to our BAT-TAB. In this case, the current phrase, when we call the function for the first time, the current phrase is the original, what the user typed in, bat tab. Hit enter to continue. Now, what we've done, and we could, if we use the debugger and step through line by line, we could see this. I just think this is an easier way to show it. What we've done is we've stripped out this B, and we've stripped out this B, and then we called the function again with ATTA, and you can see that this time the function is ATTA. Now, this is longer than one letter, and the first and the last characters are the same, so this is going to be our recursive case again. And so we can see that the next time we call the function recursively, all we have left are TT. Okay. The first and the last are the same. It's longer than one, so this is yet another recursive function call. And now what's going to happen is the current phrase is an empty string. You see nothing printed right here because this is just an empty string. The base case is now in effect. The length is less than 2. This is a 0 length string, and so we're going to return true. Okay, so we're going to hit enter, and the functions unwind themselves, and we wind up passing back true. If we want to see that more explicitly, we can print phrase length a phrase, return true, and down here we won't bother doing this for right now, but we'll just go ahead and run this code, and now it'll provide a little more detail on what's happening. So we have the recursive call with that tab. We're going to strip off the B's and call the function recursively with ATTA. We're going to strip off the A's and call the function recursively with TT. We're going to strip off the T's and call the function recursively with an empty string. This is where we were last time. Now, hopefully, the print statements will make it more clear that we got the phrase of length 0 and returned true. And then we came down here and returned is palindrome that true simply propagated up. And then alternatively, let's make sure that something is not a palindrome. This is sort of the same thing. BAT, PAB is not a palindrome, and we'll see what happens. Here, the B's are in fact the same, so we recursively call the function. Then we have the A's are the same, so we recursively call the function. Now we call the function again with TP, and you see these are not the same. So at this point, we should immediately return false. And there's no code from the base case, the other base case, it's not needed. We're simply returning false. I mentioned earlier that I would show you how to write this iteratively. I will do that now. So we'll call it def iterative is palindrome. Point of this is just to show you that the same thing, anything could be done recursively, could be done iteratively. And here it's the same thing. We have our one function, we have our one parameter phrase, checking to see if it's palindrome, iterative function to illustrate. We can solve that as well. We can solve this problem that way. We're just going to use a loop. Again, we're returning a Boolean. True if palindrome, false otherwise. Okay, so not palindrome is going to be a Boolean value just to mark whether we're still doing, while length of phrase is greater than or equal to 2 and palindrome if phrase sub 0 equals phrase sub -1, phrase dot remove, phrase dot pop -1, and phrase dot pop 0. This removes the two elements. And now we can continue with this, but we have to take care of the else. If phrase 0 is not equal to phrase 1, else palindrome equals false. Okay, and that loop will do exactly what we did with our recursion, and it will tell us whether this is a palindrome or not. And the way it is, when the loop ends, we just return the Boolean palindrome. If it's true, this is a palindrome. And if it's false, it's not a palindrome. And so what we'll do then is turn palindrome. Whatever that is, whatever that Boolean returns, that's our answer. Okay. And so what I'm going to do is I'm going to block out, comment out this call, and I'm going to say answer equals iterative is palindrome phrase. And we will try this way. So let's run this. Check to see what's a palindrome. Whoops, sorry, that should be word. This again. Yes, of course. I'm doing this on person. The correct answer here, since this is not a list, is phrase equals list slicing phrase from 1 to -1. There we go. Now we're back to working correctly. So the point of that, other than showing that it's really easy to make errors in your code when you're doing things live, is to show that you can solve anything recursively. Anything done recursively can be done iteratively. Now what I'm going to do is I'm going to switch back to sharing the Google Chrome, the slides. There we go. And look at another example. Here's the pseudocode that we've just implemented. We're going to look at one more recursive example, which is writing a recursive function to sum a list of numbers. Okay. We all know that we can sum a list of numbers by simply writing a loop that goes through the list and adds them up. Or as we saw on project 1, we can just invoke the function, the built-in function sum, and have it do it for us. But what we're doing here is simply, running a loop to add it up. But just for an interesting case, we're going to write a recursive function that sums it. Now, what is the base case of a list of numbers? And it turns out to be just like a palindrome. The base case is the sum of a list of 0 numbers is 0. The sum of a list of one number is that number. The recursive case is if we have more than one number, we can take out the first number from the list and add it to the sum of the previous. So, for example, the sum of 1, 2, 3, 4, and 5, we can pull out the 1 and say whatever that is, that's 1 plus the sum of 2, 3, 4, and 5. Well, 2, 3, 4, and 5, that's 2 plus the sum of 3, 4, and 5. So now this is 1 plus 2 plus the sum of 3, 4, and 5. Then we call recursively and take out the 3. We call recursively and take out the 4. And then we have ultimately the, we get ultimately to a list of one number or an empty list. So let's go back to PyCharm. And I'm actually going to create a new file. And it's going to be called April 11 coding 2.py. The recursive version of the sum of list of integers problem. Okay, our main program here, rather than ask for the user to enter it, I'm just going to start with numbers equal, and it's going to be a list of 1, 2, 3, 4, 5. This way I don't have to worry about reading in values, creating a list, converting them to integers, and what have you. I'm going to call my function sum numbers. And so I'm going to say answer equals sum numbers of the list numbers. And then when I'm done, I want to print answer. So now let's write that function sum numbers, which has exactly one parameter, which we will call nums. Write our comment block for this recursive function. Recursive function that sums a list of numbers. Integers in our example, but floats, it would work identical. There's no way. Our one paren nums is a list of numbers which we will find the sum. And our return integer or float as appropriate, that is the sum of the list. As long as it's a number, it doesn't matter whether it's an integer or float. Python will convert to the appropriate type. Let's do this an easy way. Base case first. If length of nums equals 0, and I forgot my colon, return 0. Now, the simplest case, I don't have to worry about 1 as a separate thing. I can even lump 1 into recursive case. We'll do it that way for now. Else, return nums sub 0 plus the sum of numbers of, and here I'm just going to chop the first value off my list. The way I chop my first value off my list is nums square brackets from 0 to the end. Here I don't chop 1 off the end. I'm just chopping the first number off here. I don't chop 1 off the end. So instead of 0 to -1, like we did on the palindrome problem, it's just 0 to the end. Okay. So let's run this program. And see what I did. Okay. Maximum recursion depth exceeded. Line repeated 995 times. Oh, because this is not a 0, this is a 1. And that was a demonstration of how to quickly exceed your maximum number of recursions and have essentially an infinite loop that Python will close for you. But again, it happens. Okay, so in fact, the sum of 1 plus 2 plus 3 plus 4 plus 5 is 15. If we want to see how this is happening, we can say A equals nums sub 0 plus some numbers 1 nums from 1 to the end. Print current sum equals A. And now we're just going to return A. Okay, and so this will illustrate where we are. And you can see that the way the function works, 1, 2, 3, 4, 5, it removes the 1, then it removes the 2, then it removes the 3, then it removes the 4, then it removes the 5, and gets to an empty list. And so now it calculates that the current sum is a 5, 5 plus the empty list 0. Then it adds the 4, the 12, the 3, the 2, and the 1. So it adds the values back in reverse order. If we maybe want to make that clearer, what we would want to do is we add in print current number is A, comma, current sum equals A. And it helps if you put your quotes back in there. Let's run it now. Here you can see, fix that. Exactly the wrong thing. Here you can see what we've done. Because we pull the 1 out, then the 2, then the 3, then the 4, then the 5, each time we're adding back in the 5, then we're adding back in the 4, then we're adding back in the 3, then we're adding back in the 2, then we're adding back in the 1. Okay? And so this is an illustration of recursively where I just chose to have one base case, which is a length of 0. If I wanted to take as a base case that a list of length 1 is also, it's just the answer is just that first number, then I could simply add in here elif length of nums equals 1, print only one list item to show you where we are, and return nums sub 0. And if I run this, then you can see we still get the same answer. Okay. The only one list item occurs when we're down to the value of 5. The value of 5 is not printed because we're being addressed by the other base case, not the recursive case anymore. This is where it's 5. Then we get the 4, the 3, the 2, and the 1. The principle is the same. The recursive case, we strip off the first list element, and we have this, and then we recursively call on a shorter list. Going back to our slides, this is a case where everything works fine because we have a base case, at least one. We have a recursive case, and the recursive case is simpler. We're finding we're the sum of a shorter list. The first case, we had a list of 5 numbers. The second case, we had 4, then 3, then 2, then 1. Every time we wound up making the list simpler. So again, bottom line, recursion, it makes some problems simpler. We can always solve it iteratively, but recursion just is a nice thing to know because there are some problems it's a natural fit for. Recursion is going to work at least one base case, at least one recursive case. Recursive case has to get you to a base case, and it has to give you a solution to the problem you're actually trying to solve. It has to be a solution for the right thing. The other thing I wanted to talk about in this recording is homework 6, because homework 6 is available. You have a week from today to do it. It's due the 18th. I know you're also going to be just finishing project 1 and working on project 2, but we need to get this in. It's tight in the schedule. This is your last homework. The only thing you have left now is projects 2 and 3. This is the last homework, but let's talk about it. It's available in the class GitHub. It is the same as the majors. The majors have to have this done this Friday, the 15th. You have until the 18th. It's 40 points. You can possibly get extra credit on the assignment. The bottom line on this is the function, the purpose of this homework is to teach you recursion. Yes, we've known, we've demonstrated, we've discussed. You don't have to do it recursively. You can always solve all of these problems iteratively. Okay, but for this homework, you have to use recursion. If you don't use recursion, you're going to get a 0 on that part. So pay attention and use recursion. As with everything else, there are 5 problems. Submit them using the standard way. Coding standards, what you can use and what you can't use. You've seen this by now. Pretty much everything you've seen is now permitted. The only things forbidden are things we either consider bad programming practices like break or continue, or methods we just haven't covered yet. All kinds of lambdas and globals and things like that. No importing importing libraries, no using classes or object-oriented. We haven't covered that yet, and you don't need them. Okay, so the bottom line is each of these 5, identify the base case, identify the recursive case, write the code, and test it to show that it works. So recursive range, simulate the range functionality in recrange.py. We call rec range return a list of the proper elements. So this is, if you think of a for loop, right? A for loop says for I in range 0, 5, 1. That means evaluate this where I is 0, 1, 2, 3, and 4. We want you to convert that idea to recursion. So you're going to use recursion to generate that list of, we need to do this with I equals 0, 1, 2, 3, and 4. Okay. This is kind of a guided one. Let's talk about what the base case is. Base case is, well, it's an invalid range, right? If start is greater than end and step is greater than 0, or start is less than end and step is less than 0, we're just going to return an empty list. That's if I say for I in range 10, 5, 1, that for loop will not execute because the start value is greater than the stop value, so we never actually do anything. So that is a base case. A base case is simply that this is never going to run because of the conditions. Okay, now recursively, we have to call it. So what we're going to do, similar to the 2 examples I've just shown you in this video, we're going to get a new start parameter. We're going to jump up the value by however many the step is, 1, 2, whatever. Okay, and so recursively, we're simply going to say, well, what values in for I in range start, step, stop, step, we're going to figure out what values of I are actually going to be executed. And we're going to do it, as I said, recursively. We're going to take the next value that's going to be executed, and you can see here, right? If originally it's 0, 5, 1, we know this gets evaluated where I is 0. jump up by 1. Yeah, I gets evaluated where I is 1, 2 is still less than 5. It gets evaluated where I is 2, then 3, then 3, then 4, and so on. And finally, we're going to get down to a base case. And so the bottom line is we're going to generate the list of all the values of I that I would actually be executed for in our for I loop. The code here is a test driver you can test to make sure it's working out. Okay. And you can see how it happens here. Catalan numbers is defined given this formula. So you basically have to implement this formula. You know that C0 is 1. Gee, C0 equals 1. That sounds like a base case. So C1 is 2 times 3 over 3 times 1. That is, if Cn plus 1 is 1 and Cn is C0 is 1, so C1 is 2 times 3 over 3 times 1, which is going to give you 2. So the rest of this is simply going through and implementing the code. The caution, be very careful about order operations, is simply operator precedence. Multiplication, division, addition, etc. Do your things in the parentheses first, then do multiplication, division, left to right before you do addition, subtraction. Okay. Another test driver. Slice replace is recursive. It simply goes through strings and removes specific values and replace them with other values. Okay. And the first example, we're going to go through, you're going to go through this string and replace every occurrence of EL with X. Then you're going to go through this string and replace every occurrence of AB with C. Okay. And that's fairly straightforward. What you do is you just go through the string and you remove, every time you make a change, you remove. Problem 4, count gold. And problem 5 is look for A and B consecutive in a string. Again, fairly straightforward. It's a matter of what's the base case, what's the recursive case. So the first of our problems, we gave you base cases and recursive cases. For the rest of them, you have to figure it out. Please, between when you watch this video and Wednesday's lecture, be thinking about them so that if you have any questions on what the base case and recursive case on this, you can be ready to ask them. So at this point, I'm going to end this recording. This will be posted on the YouTube channel as you found if you see it. And I will post another video to talk about Project 2. And then I will see you all again on Wednesday. If you have any questions, you know how to get in touch with me. So thank you very much. And at this point, I will stop the recording and end the video. Thank you.